Okay, so the question we have today is let x1, x2, be IID random variables with probability density function, well, with an exponential distribution, which has a PDF, lambda e to the power of negative lambda x. Now we suppose that n is a geometric random variable with this probability mass function, where p is between 0 and 1, and denote s to be the summation from I equals 1 to this big N here of all of these different random variables. So find the moment generating function of S given N equals N. Right, so this is relatively simple. So for A, we want to start off, as typically do in mathematics, with the definition. So what is the definition of the moment generating function of S given N? Now, a moment generating function is a function of this t random variable, and it is the expectation of e to the power of ts. Now in this case, why is it s? Well, s is the function, the variable that we're looking at. And well, we can be a little bit more specific here, given n. I don't think that's an abusive notation. Maybe it is, but this may be wrong. It may just be like e to the power of tx. And I'm not sure whether or not you're allowed to put this conditional on here, but just to be precise, we're going to be using it. So, yeah. So we're going to continue on, but we're going to remove it just for the sake of, I haven't seen too much of that. So we're going to sub in, now what is S? S is the sum of, from I equals 1 to n, of all these different xi's. And then we're going to do some algebra to get tx1 plus dot 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 plus txn. Now, you can, I'm doing some more algebra here. You can write this all the way out. I'm going to do that. And you get this, say, expectation of e to tx2 dot 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 e to the power of e txn. So what is this? Well, in order to find what this e to the tx1 and all these different components are, what is e to the power of tx1? Now that is the definition of the MGF of x, or rather just the moment generating function of x1, and then this is the moment generating function of x2, and that's the moment generating function of xn, etc. So how do we calculate this? Well, you again use the definition. So the expectation is going to be this, because, well, the integral from 0 to infinity, and then e to the power of tx. Now, I'm not going to use tx1, I'm just going to use tx just for, well, a little bit of abusive notation, but it is okay. And then I will not be doing this integral. However, it does come out to lambda minus t. I just did the integral like 10 minutes ago, and I don't want to do it again. But the overall framework is there. Now, what you can do after you've calculated mx1 is say that because x1, x2, x3 are identically and independently distributed random variables, it means that also mx2 t is going to be lambda over lambda minus t, and then etc. with, well, the moment generating function of xn is going to be this also. And so the moment generating function of s given n is going to be equal to lambda minus t to the power of n. Okay. And so the second question is find the moment generating function of s. Now this is very interesting. Now first, we're going to start off with the definition of the moment generating function again, and then I'll go into a little bit more explanation. So the moment generating function of s is e to the power of st, right? But it is also the expectation over n of the expectation of e s st given n. So what does this mean? It means we're basically taking the moment generating function of we're taking the expectation of s. Yes, we're taking the expectation of s given n. Okay. Let me say this as precise as possible. That correlates with how I'm thinking about this. We're taking the expectation of s with respect to s given n over here in the inner expectation. And then in the outer expectation, what happens is we've taken the s out of the picture, and we're left with, okay, well, we really just taken the expectation of this with respect to s given n. And then afterwards, we're taking the expectation of s, but over n. Oh my gosh, that was horrible. Well, ChatGPT or Gemini could probably explain this to you better, but that's what we're doing. All right, so now we have I equals 1 to n. Now, why is it discrete this time? It's because n is a discrete random variable. And so we're going to use the definition of expectation here. Now, in this case, we're going to use k. Now, why do we use k? It's because k is the notation we're using to denote the value that n takes on. And then obviously we're going to put in the probability associated with k. With n. All right. Now, how do we continue forwards here? Well, we have a few different options. We're going to do I equals 1 to n lambda minus t to the power of k, and then 1 minus p to the power of k over 1 minus p times p, and then we get, p I equals 1 to capital N of lambda 1 minus p lambda minus t to the power of k over 1 minus p. And then we're going to do another algebra trick with summations. We're going to let I equal to s plus 1. We're going to do that. I equal to s. So then s equals I minus 1. So s plus 1. Oh, in this case, it's k. We're doing k. K equals. Oh my gosh. Wrong subscript here. K equals 1. K equals 1. K equals 1. And then, well, we'll change this to k and then k. And then what do we have? We have after we make this change here, we have p to the power of s plus 1 equals 1 to the power of n, and then lambda 1 minus p, lambda minus t to the power of s plus 1, and then 1 over 1 minus p. And so we get p s equals 0 to the power of n, and then lambda 1 minus p, lambda minus t. And what we're going to do is take out the extra bit. So lambda minus p, lambda minus t, 1 over 1 minus p. And then what we're left with is p, the sum of, well, that's a horrible p, p s equals 0, the power of n of lambda 1 minus p, lambda minus t to the power of s times, lambda over lambda minus t. Because these are constant with respect to the summation s, we can do p lambda minus t times lambda, and then the sum of this, lambda 1 minus p, lambda minus t to the power of s. Now, if we recall, the summation, well, actually, this isn't to n, it's to infinity. It's to infinity here. And why is it to infinity? Is it to infinity? With a random variable. Oh yeah, it is to infinity. It is. Dang it. Infinity. Okay. Infinity. Okay. We get p lambda minus t, and then one well-known fact about these types of this is x equals 0 summations is that you can use a formula and it equals to this, lambda minus t. And then what you can do is just multiply these two terms together, and you get lambda minus t minus lambda plus lambda. Wait a second. Let me do this again. Lambda minus t minus lambda plus lambda times p. And then these two lambdas cancel out, and then you're left with lambda p over lambda p minus t. And so this is the moment generating function of s. Oh my gosh. Okay. Now, one more bit. The mean and variance of an exponential distribution. Now, if you, well, what is the mean and variance of s? In this case, the moment generating function of s is equal to the moment generating function of an exponential distribution with parameters p lambda. So in this case, the mean is just going to be, well, 1 over p lambda because we're using the scale parameter, the right parameter. And then for the variance, it's just going to be the square of this. So the variance of an exponential distribution is just the square of its mean parameter. So in this case, 1 over lambda squared, p squared. And so that is a question. Yeah. Yep.